Okay, so I'm going to go over the basics of Euler's method. So basically what you need to know is that this is a method that's used for estimating. So all you're doing is estimating a certain point. And for all these problems, you're going to be given a differential equation, you're going to be given an initial point, and then you're going to be given a point that you need to find. So basically what this method is doing is it's giving you a point, say right here on the graph, and it's giving you the differential, so the slope at that point. And then from there, you're just estimating, okay, so there could be a point right here, and then you get the derivative of that point so that you can estimate another point until you find the point that you need to find. So I'm going to go over two examples of this, and the first one will be really easy, and the second one will be more challenging. Okay, here's example number 1. Now this is the easier one, and you can tell it is already setting everything up for you. It gives you all the information you need to know. It gives us the step size, so that's already a lot easier, the point we need to find, and the initial point. So we can already start setting up our table, which would be xy, the derivative at that point xy, the change in x, the change in y, and then x plus the change in x, and y plus the change in y. Now, to find the first point, we use the initial values it gives us. So this would be 1, 0. And now, to find the derivative, all we have to do is plug in this point into the differential it gives us. So in this case, this one only has y, so we only need to plug in the y. So it'd be 0 plus 1, which would just equal 1. So this would equal 1. And to find the change in x, it gives us the change in x right here in the step size. So this will be 0.5. And to find change in y, all you have to do is multiply these two together. So this would be 1 times 0.5, which equals 0.5. And I'll make this a table just so it looks neater. All right, and now we just add them. So we take 1 plus 0.5, which would be 1.5, and then 0 plus 0.5, which is also 0.5. And we bring this point down, and we're going to do the same exact thing, but this time with different points. So once again, we plug 0.5 into here, which will get 1.5. We keep this the same, because it's the same step size. Change in x will always be the same, and then we will multiply these, which will be 0.75, and then we just add them again. So this would be 2, and this would be 1.25. And that's our answer right here. F of 2 is about 1.25. Now that one seemed pretty easy, but I'm going to go over the next problem, which is more like what you'll see on the test. And that one's a lot more complex. Here's our next problem, and as you can see, it's already looks a lot more difficult, and it's a lot more test-like. So it says, let f of x be the solution to the differential equation, dy dx equals 3x plus 2y. So that's our differential equation. And here's our initial condition. It says with f of 1 equals 0.5. And we're finding the approximation of f of negative 1 with 4 equal steps. So first thing we need to do is we need to find what's our step size? What is our change in x? And to find your change in x, all you have to do is take your end point, minus it by your start point, and divide it by the number of steps it tells you. So in this case, we have our start point right here at 1, and our end point right here is negative 1. So negative 1 minus 1 divided by the number of steps, which is 4. So that means we'll get negative 2 over 4, or negative 0.5. So our step size is going to be negative 0.5. So now we can already start setting up our table. So our table is going to look like x comma y, dy dx at that point, x comma y, the change in x, the change in y, x plus change in x, y plus change in y. So now we have this, and we know I have to do 4 equal steps. So it's going to be 0.5, negative 0.5, negative 0.5. And we're starting at 1 comma 0.5. And our differential equation, I'm just going to write here to make it easier to see, is 3x plus 2y. So now that we have this problem set up, all you have to do is start calculating. That line was really bad. Okay, so we just plug in 1 times 3 is 3, plus half of 2 is 1, so this would be 4. This would be negative 2, and we just add, it would be 0.5, and then negative 1.5. And then we just bring this down and we keep on going. So we plug this in, it would be 1.5, and this would be negative 3, so negative 2.5. And as you can see, the math is going to get more and more complicated, so you probably have to use a calculator here. Just give me 1 second while I grab a calculator. Okay, I finally got a calculator. So we're going to do negative 2.5 times 0.5. That'd be... And then we just keep going across. So this would now be 0, and this would be 0.25. And we would continue this pattern until we get to the end. Now I'm kind of regretting picking a problem with 4 step sizes. So this would be 0 plus a quarter of 2, so that'd be 0.5. This would be 0.5 times 0.5 is negative 0.25. Now we have negative 0.5 and 0. Then on to our last step, we have negative 0.5, comma 0, which this would be negative 1.5. This would be 0.75. And this would just be negative 1, comma 0.75. And that's our answer. We finally got f of negative 1 is about 0.75. So the key takeaways here are, to find this column, you plug it in to this equation up top. To find your x, change in x, you plug it into this formula here. To find your change in y, you're just timesing the derivative times your change in x will equal your change in y. And then this column here is pretty self-explanatory. You're just adding this x here and your change in x together. And then this y here to your change in y. All right, well, that's the basics of your Euler's method. If you still need any help on anything, just let me know.